Observing the moon, a sunset, or the night sky means being captivated by the past. Because, as astounding as it may be, with its 300,000 kilometers per second, the light emitted or reflected by an object always has a limited speed. Thus, from Earth, do we actually only see our satellite as it was a little over a second ago? Our Sun, 8 minutes and 18 seconds ago, the pillars of creation about 6,000 years ago. Some 60 centuries of travel at the staggering speed of 300,000 kilometers per second were necessary for light to cover the distance that separates these columns of interstellar dust from the mirrors of our telescopes. The grains of light that reach us left this region of the sky at a time when we had not yet invented writing. And they have traveled through silent space throughout all of antiquity, the Middle Ages, the Renaissance, and the modern era, before coming to strike our retinas. The photons we receive from the Andromeda galaxy left it when our ancestors were just starting to walk. Space is so vast that, to talk about the distances that separate us from the objects found there, we use light time as a unit of measurement. The pillars of creation show us what they were, and it might be more accurate to talk about them in the past tense and say, "This nursery of stars was beautiful at the moment when the light that now reaches us left it." Perhaps the pillars no longer look like this because a nearby giant star is about to explode. It's possible it has already happened. We don't know if these pillars still exist or if they have been distorted or blown away by a shockwave produced by a supernova. And it's possible that the light, the image of this spectacular explosion, is currently traveling through space, heading towards our eyes. Not being able to know precisely what things look like right now also makes light an amazing time machine. Because the further away what we observe is from us, the further back in time we go. And if we want to see what our universe looked like, for example 6 billion years ago, we simply need to observe stars that are 6 billion light years away from us. Not only does it allow us to see what the universe looked like at times so far back, that neither the Earth nor the Sun even existed yet. Light also acts for us as a key, whether it comes from a lighter flame or a star. Located several billion years away, it gives us their temperatures, densities. Like fires, red stars are colder than blue ones. And then, studying light has allowed us to discover that we live in a world where the majority of everything that can be seen is inaccessible to our eyes. Here is the vast array of the electromagnetic spectrum, which includes all ranges of light that exist. The very small part to which our eyes are sensitive is here. This is the realm of the visible. The rest, all the rest is invisible to our eyes, as if nature was putting on a show on a stage where the curtains are practically closed for us. In the same way that a musical chord is made up of several notes, when a star shines, it emits in several ranges of light. Our vision, like that of all species on our planet, has evolved and adapted in an environment bathed in a particular light that produced by our sun. And in reality on Earth, it would be more accurate to say that the curtain for us is somewhat half open, because our eyes are capable of perceiving nearly half of the radiation emitted by our star, of which 45% of the energy it emits is within this small band. Here lies all the richness of colors and nuances of our daily life. Despite everything, more than half still eludes us. 46% of sunlight falls into the so-called low-energy and long-wavelength category, such as infrared, microwaves, and radio waves. And the remaining 9% falls into the high-energy and short-wavelength lights category, where we find ultraviolet, X-rays, and gamma rays. In the visible range, as seen from space, our star is not yellow or red, but a brilliant white, in which a multitude of colors and wavelengths are mixed together, which can be dispersed using a prism. Because when traveling inside it, light waves begin to move at different speeds and separate, drawing what are known as Fraunhofer lines at the exit. It took us a long time to decipher these lines, and what we discovered is that this decomposed light once again acts as a key for us. These ribbons of colors hold a secret. They can reveal the composition of objects. To the naked eye, between these two flames, you are likely to see red. But a spectrograph capable of studying its light can tell you if. These fires are produced by the combustion of butane from a lighter or wood from a match. Because, depending on its nature, the matter surrounding the flame disturbs the rays that reach us. We thus realize that each element, each atom, has a unique spectral signature. In a way, its light footprint allows it to be identified. And this works with any object, whether it's on Earth or elsewhere in the universe. Whether you're looking to know the composition of the atmosphere of Venus, Jupiter, distant galaxies and stars, or interstellar gas clouds. As long as the object being studied reflects or emits light, it is possible to know what it is made of without needing to touch it. To take a sample of the sun, all you need to do is look at it. Here, after its light has passed through our atmosphere, is the signature of our star. This colorful identity card is an open book that tells a story, that of the sun's composition. The black lines present here inform us about the parts of the electromagnetic spectrum that are not emitted by the sun. In other words, on what is there or is not there. And by studying the billions of stars that populate our sky, whether they are close or terribly far away. These Fraunhofer lines also reveal to us that the entire visible universe is made up of the same elements that we find on Earth, but in different proportions. They have even allowed us to discover new elements from a distance. In 1868, by observing the sun's spectrum, a wavelength was discovered that did not correspond to any known atom. A new atom had just been discovered there, which was named helium, from the Greek helios, the sun. Our star is made up of nearly a quarter of this element, but it is so scarce on Earth that it would take another 15 years before it was found there. Today, as long as you have a mass spectrometer at your disposal, you could even deduce it without having to touch it. The composition of a person by simply analyzing the light they emit. Well, the problem is that this machine studies the ionized gas phase, so to study it, you would need to be able to vaporize your subject. And then, being able to study other types of radiation also allows us to reveal hidden structures and the inside of things. Because, depending on their wavelength, lights do not behave the same way with matter. The clouds of gas and dust, which make up the Horsehead Nebula, strongly absorb the light rays in the visible domain. But if we observe this immense structure in the infrared, then whole sections of a reality that previously eluded us are revealed. Here, at the base of the head, young stars in the process of formation make their appearance. In the same way, if we observe the Carina Nebula in the visible domain, many stars there are discrete. But if we switch the SEN to infrared, then suns hidden in deeper layers reveal themselves. Because this low-intensity light can largely pass through the clouds that surround them. Ultraviolet rays, however, have difficulty penetrating our atmosphere, which is beneficial for us. As for radio waves and microwaves, the Earth's atmosphere is, for this type of light, as translucent as glass, to the point where we can study the sky in this part of the spectrum from the ground using radio antennas. Depending on the types of rays that manage to make their way and how they do it, we can access a lot of information previously inaccessible to our eyes. As we are reminded by X-rays, which play through our flesh, and like gamma rays, they have very high energy and short wavelengths, thus interacting strongly with matter. To the point where, to protect yourself from this type of rays, the kind of sunscreen you need is a reinforced door made of steel or lead. Although an atmosphere 100 kilometers thick like ours also does the job. Because this protective layer has the same effects on its rays as 5 meters of concrete would have. And that's why trying to observe gamma and X-rays coming from space at ground level is almost always met with radio silence. Which is a good thing for us, because without this protection, all the high-energy radiation would pierce us like so many little deadly arrows in the long term. But as we gain altitude, the thickness of the atmosphere above our heads decreases. As it decreases, the X-rays and gamma rays from the sun or other distant stars become more present. That's why, on a plane, 5 round trips from New York to Beijing. It's the equivalent in radiation exposure of a pelvic X-ray. And to finally study this type of light, without it being disturbed by the atmosphere, you actually have to go into space. There, our galaxy becomes nearly unrecognizable. Sand. Because observing the sky in the field of high-energy lights is to highlight the most energetic phenomena of the universe. To convince ourselves, let's head towards the Crab Nebula, a region of the sky where a young massive star recently exploded. By observing it in the field of X-rays, we realize that here in the center hides a strange object, the remains of the crushed heart of a now disappeared star. A rapidly rotating neutron star whose powerful electromagnetic pulsations reveal its presence through the ripple-shaped disturbances they exert on the surrounding gas. So light is a key to understanding nature, a key that allows us to go back in time, see through things, and know what they are made of from a distance. And icing on the cake, to learn a lot about the movement of objects. Because the light emitted by a star or a galaxy allows us to determine its speed and direction. It is influenced by their movement relative to us. And if these objects are approaching at high speed, then the wavelengths of the light that reaches us are shortened. Conversely, if they are moving away, they are stretched. This phenomenon, called the Doppler effect, is observed for both light and sound. In fact, it is often illustrated never by the example of a diva attached to a rocket, and whose screams would seem more acute as she approaches you and more serious as she moves away. The Doppler effect, among other things, led us to discover that our universe is expanding and that this expansion is accelerating. Because we have been able to observe that beyond a certain distance, the further galaxies are from us, the more the light that reaches us has a stretched wavelength and shifts towards red. In other words, the greater the distance that separates us, the faster it seems to flee. But the greatest of all discoveries that we owe indirectly to light is perhaps the evidence of something we can't even see. And that in no wavelength. Dark matter. The presence of this matter that emits, absorbs, and reflects no light was able to be demonstrated always by the Doppler effect, by noting that the stars rotate abnormally fast around the center of their galaxy, and that the movement of these relative to each other suggests the presence within them of an exotic matter accounting for 5 times the mass of all the ordinary matter found in the universe. And the fact that there is a great mystery there, a matter about which we currently know almost nothing except that it must be there, comes to us once again from the properties of light, which, taken in the larval sense, in the sense of the entire spectrum, literally bathes all things. In fact, we are even a source of it. Because any object that has a temperature, and I hope you have one, emits light in the infrared range. From that perspective, we radiate. An idea that would surely please some ancient Greeks who thought that sight came from the emanation of light rays projected by our eyes and going somewhere, like illuminating objects. And as I see nothing to add to this curtain of light, do you think that at 4.5 billion years from here, is there someone or something watching our sun form? And who are wondering, why do you have a big head? I read a paper from a researcher who had fun calculating the size our eyes and pupils would need to be in order for us to see radio waves. He proposed around 5 meters. I tested it to quickly determine if we have a strong Wi-Fi connection. And it works. No? You bit off more than you could chew. To me, you have a butt face, so it's a success. Heartfelt thanks to all the tippers. To keep the light on all floors, remember to activate the bell so you can follow the entire series.